In this video cast, we'll look at formula weights, percentage composition by mass, and Avogadro's number in the mole. Make sure you have these notes in front of you, and also make sure that you have your calculator handy while we do some of these sample problems. First of all, chemical formulas and chemical equations both have a quantitative significance. In other words, the subscripts in the formulas and the coefficients in the equation represent precise quantities. One of the things that is represented by a chemical formula, or can be found from a chemical formula, is its formula weight. The formula weight of a substance is the sum of the atomic weights of each atom in its chemical formula and can be found by looking on the periodic table. Make sure you have a periodic table in front of you right now while we do these sample problems. Formula weight is also known as molecular weight if the substance is molecular. In other words, it's made of only non-metals. Sometimes it's also called formula mass or molecular mass, which is actually technically a little bit more precise or a little bit better name. So get used to these four things, all meaning the same thing. Formula weight, formula mass, and molecular mass, as we'll see when we use them on the periodic table. For example, take the formula H2SO4, known as sulfuric acid. We can find the formula weight by taking the atomic mass of hydrogen on the periodic table. And if you look at hydrogen on the periodic table, it has an atomic mass of 1.008. And there are two of them in the formula, so 2 times 1. I'm approximating the atomic weight of hydrogen at 1, even though it's 1.008. I'm going to approximate it as 1. Adding it together with sulfur, and if we look on the periodic table, sulfur has an atomic weight of 32.07. So we add that to the sulfurs, which there are one of them, and it's about 32, so I'm going to approximate that. And add that together with the 4 oxygens that make this up. And oxygen, if I look on the periodic table, has an average atomic mass of 16. And we'll have to multiply that by 4. 16 times 4, because there are 4 oxygens. When I add these together, I'll have the average atomic mass, or the average formula mass, or the average molecular weight, I could call it as well, of H2SO4. And if I add those all together, the formula weight of H2SO4 is 98, or if I used the decimals, it'd be about 98.1. And the units for this would be atomic mass units, because remember, atomic masses of elements on the periodic chart are given in atomic mass units. We'll find out a really handy relationship between these numbers and things that we can macroscopically measure as well. Remember, atomic mass units are kind of small. Let's try this one as an example problem. C6H12O6. If I wanted to find the formula mass of this, I would take 6 times whatever carbon's atomic mass is. And if I look on the periodic table, carbon has an atomic mass of 12, and you'll get quick at memorizing some of these and knowing what they are fairly quickly. Plus hydrogen, there's 12 of them once again in this formula, and I need to multiply that by hydrogen's atomic mass, which if I look on the periodic table is 1.008, which is pretty close to 1, plus oxygen's atomic mass, and I need to multiply that by 6 because there's 6 of them, and 6 times 16 because oxygen's atomic mass is 16 if I look at it on the periodic table right here. So make sure you've got your periodic table in front of you, because we're going to do this a whole bunch of times. If I multiply these together and add them up, it turns out to be 180 atomic mass units. Now I can use these additions to add up the formula weight or molecular weight, or formula mass or molecular mass, to find out the percentage by mass composition of nearly any substance for which I know the formula, using the atomic mass units or the formula or molecular weight on the periodic table. First question says, calculate the percentage of carbon, hydrogen, and oxygen by mass in C12H22O11. Well, to find the percentage of something, what I need to do is take the part that I'm interested in, and divide it by the whole thing. So I need to find the whole mass of C12H22O11, and that'll go on the bottom. And the part that I want to know, in other words, just carbon in the first part of the question, hydrogen in the second, oxygen in the third, and put that as the part on the top. And then I need to multiply this, I should make this a multiply sign, by 100%. And the percentage is just like a set of units. I'm not multiplying by like 0.01 or 0.1 or something like that. I'm actually multiplying by 100. So if I add this up on the periodic table, C12 12 H22O11. Carbon is worth 12, and there's 12 of them right here. H is worth 1, and there's 22 of those here. And then oxygen is worth 16, and I need to multiply that by 11 because there's 11 of them. And if I multiply that all together, I end up with 342 atomic mass units. Now this is the whole thing of C12H22O11. Now if I want to find the percentage composition, what I'll do is take the part that is carbon, and in this case it's 12 times 12 because the atomic mass of carbon is 12. I can look that up on the periodic table right here. Here's carbon and it's 12. And then I'll multiply that by the number of carbons in the formula, which is 12. 12 times 12 is 144. And divide that by 342, which is the whole thing, and multiply it by 100%. So 42.1% carbon. Now, I could also find out the percentage composition of hydrogen and oxygen. And if I wanted to find hydrogen, it would be 22 divided by 342 times 100. And that would turn out to be 6.4%. And if I wanted to find, that's for hydrogen. Now, if I wanted to find oxygen, oxygen is equal to 16 times 11, because there's 11 in there, divided by 342. Multiply that by 100%, and that would turn out to be 51.5%. As well. Even the smallest samples that we deal with in the laboratory contain enormous numbers of atoms, ions, or molecules. For example, a teaspoon of water, about 5 milliliters, contains 2 times 10 to the 23rd. 2 times 10 to the 23rd molecules, a number so large that it almost defies comprehension. Chemists therefore has devised a special counting unit for describing such large numbers of atoms and molecules. In everyday life we use a word like a dozen to be a counting unit, and if a dozen is equal to 12, we could say we have 2 dozen eggs, which would mean we actually have 24 eggs. 1 dozen is actually a type of counting unit. Well, in chemistry, we use a unit that's called the mole, M-O-L-E, and 1 mole isn't equal to 12 like a dozen is, but a mole is equal to 6.022 times 10 to the 23rd. 6.022 times 10 to the 23rd. Scientists call this number not only the mole, but they also call it Avogadro's number. This is in honor of Amedeo Avogadro, who lived in the late 1700s until 1856. He's an Italian scientist. And we'll approximate it as 6.02 times 10 to the 23rd for the most part throughout the text. So what we like to be able to do is to figure out the number of atoms or moles of atoms in many samples of things. And if we know that in 1 mole of something there are 6.02 times 10 to the 23rd things, this gives us a conversion factor between the microscopic world, or nanoscopic, I guess, since we're talking in terms of atoms, and the macroscopic world that we actually live in, because we can't actually see this many things, but we can see lots of these different things, and so we'll call it a mole of that substance. So the first question is to calculate the number of hydrogen atoms in 0.35 moles of C6H12O6. And to do this problem, what I'm going to do is I'm going to first write down the number that they give me, 0.350 moles, and I'll put a multiply sign and I put a line. And I want to know how many hydrogen atoms there are in this formula. And if I look, there are 12 hydrogen atoms in one of these formula units, or in 1 molecule of C6H12O11. So the first thing I'll do is I'll convert to molecules or formula units of C6H12O6, which is called glucose. And the relationship that I just learned is that in 1 mole there are 6.02 times 10 to the 23rd things. So I'll put my mole in a position where it's going to cancel, and I'll put molecules, mole is abbreviated MOL, by the way. I'll put molecules as my new set of units. And I learned that in 1 mole there are 6.02 times 10 to the 23rd. So 6.02, and I'll just write it as E23 molecules. Now this is molecules of C6H12O6, and the question asks how many hydrogen atoms are there. So I need to do a second portion to this. I'll put another multiply sign and another line, and in this case what I want to do is compare the hydrogens now to the formula units or the molecules of C6H12O6. So I will put and say in one molecule, notice how I put my units in first of C6H12O6, and I'll have those cancel with each other. There are 12 hydrogen atoms. Where did I get that 12 from? Well, there's a 12 right here below the hydrogen. Notice my molecules cancel with my molecules, my moles cancel with my moles, and I end up with hydrogen atoms right here. And if I multiply those together on the on my calculator, 0.35 times 6.02 times 10 to the 23rd times 12, I end up with 2.53 times 10 to the 24th hydrogen atoms. That's one example of how we can use the mole as a counting unit to tell us how many things or how many atoms, molecules, or ions there are in a substance. Let's do a second example of that. This one says how many oxygen atoms are in 0.25 moles of CaNO3 Well, I'll start with the number that they give me, 0.25 moles. And this is moles of CaNO3. Always put your units in first. Put a multiply sign, put a line. And it's asking for oxygen atoms, but the first thing I need to do is figure out how many formula units of this CaNO3 there are. And so I'll put mole in a position where it's going to cancel, and I'll put my formula units of CaNO3. And the reason I call it formula units, remember, is because this is an ionic compound, not a molecular compound. Otherwise I could say how many molecules of CaNO3 there are. And it turns out that in 1 mole, this many, 6.02 times 10 to the 23rd formula units of CaNO3 exist. Notice I have my mole now canceling with the mole, and I'm going to be able to find out how many formula units of CaNO3 I have. The question doesn't ask for how many CaNO3 there are, though. It asks how many oxygen atoms there are. So I need to relate CaNO3, the units that I have, put that in a position where it's going to cancel, to how many oxygen atoms there are. And if you look, there's 3 times 2, or 6 oxygen atoms in one of these formula units. So it's a ratio of 6 oxygens to 1 formula unit of CaNO3. Now if I multiply those together, it turns out that this is, or equals, 9.0 times 10 to the 23rd, and you can go ahead and pause and try it on your calculator right now and see if you end up with 9 times 10 to the 23rd oxygen atoms in 0.25 moles of CaNO3. Moving on to the next page. I promised a relationship between the molar mass, or the formula weight, or the molecular weight, or the formula mass, or the molecular mass that we started. I promised a link between that and the counting, or the ability to find out how many atoms or molecules there are of something. And this is known as the molar mass, or the molar weight. And now that we've introduced what the word mole means, we can call the formula mass, or the formula weight, also the molar mass, or the molar weight of something. Now, because carbon has an atomic mass of 12. Carbon 12 has an atomic mass of 12. We would say that there are 12 atomic mass units of weight in one carbon atom, because that's the defined atomic mass units. Well, it turns out that there's a link between atomic mass units and grams. As a matter of fact, the mass of carbon 12, one mole of carbon 12 atoms, is 12 grams. This gives us the link now between 6.02 times 10 to the 23rd carbon-12 atoms and being able to mass them out in the laboratory. Magnesium-24 isotope would mean that if I have 1 mole of magnesium-24 atoms, it would weigh 24 grams. And if I have a sample of gold 197, that would mean 197 grams of gold, as long as it was the isotope of gold 197, it would have a mass of 197, and therefore that would be equal to 1 mole of atoms of that. Notice that when we're dealing with a particular isotope of an element, we use the mass of that isotope. Otherwise, we'll use the average atomic mass of the element on the periodic table. So what does this mean? Let's do some sample problems to see how this fits together. The mass in grams of 1 mole of substance is called the molar mass, or sometimes it's called the molar weight. Here's the first question. What is the mass in grams of 1 mole of C6H12O6, also known as glucose? Well, the relationship can be written out like this, and I think it's a little easier if I take a piece of paper right now and just write out the relationship between mass and what's called the mole. Remember, the mole is a counting unit, 6.02 times 10 to the 23rd things, and the number of particles, which in chemistry class are almost always things like atoms or ions or molecules or formula units. The relationship here says that when I move from the mass of an object to the number of moles of particles of that object, what I can use is the periodic table, and my relationship going from mass to moles is going to be multiplying by a ratio where I take and put 1 mole on the top of the ratio and the molar mass or the molecular mass on the bottom of that ratio. When I move from moles to mass, now I use the inverse of that, or I put the molar mass from the periodic table on the top of the ratio and 1 mole on the bottom. Notice when I move this direction, this is the ratio that I'll use. When I move from moles to particles now, from a mole of particles to the actual number of particles that I have, now I take Avogadro's number, 6.02 times 10 to the 23rd, and put that on the top of the ratio and 1 mole on the bottom. And when I move from particles to moles, now I use the ratio of 1 mole on the top and 6.02 times 10 to the 23rd things on the bottom. Keep this handy because we'll actually expand this to have spokes or arrows going in this direction and this direction to be able to convert to volume and eventually to, well, we'll actually use electrons in chapter 20 too. But keep this handy, and some people call this the mole conversion wheel because it ends up having 4 spokes and kind of goes around in a circle. But this is the relationship, and if it doesn't make total sense to you right now, let's work some sample problems so we can help you out. First question says, what is the mass in grams of 1 mole of C6H12O6, also known as glucose? Take a look at what they give you, 1 mole. Take a look at what they want to know, the mass in grams. Now, look at the relationship we just built. They tell us we have a mole. They want to know the mass. So we're going to move from the mole to a mass, which means we'll put the molar mass from the periodic table on the top of the relationship and 1 mole on the bottom. So the way to do this, and here are the steps. First, write 1 mole of whatever it is, C6H12O6, put a multiply sign, put a line. I used the number 1 because that's how many moles they told me I had. If they told me I had 20, I'd put the number 20 right here. Then take and put the molar mass from the periodic table of the thing they told us on the top, and that will be in grams, and put 1 mole on the bottom. because we want to put the units of mole in a position where it will cancel with units of mole. Now, where do I find out the number of grams in a mole of C6H12O6? Well, I find that out from the periodic table. And this is why it's important to be able to add up what's called the molar mass or molecular weight of something. Carbon, remember, is worth 12, and there's 6 of them, so 6 times 12, plus hydrogen, and hydrogen, remember, has a molar mass or atomic mass, of 1, and there's C6H12 of those, and oxygen has an atomic mass of 16. And if you remember back to the page before, it turned out that when I add up 6 carbons, 12 oxygens, and 12 hydrogens and 6 oxygens, it added up to be 180 grams. So 1 mole times 180 divided by 180 grams divided by 1 mole. Notice the moles cancel with the moles. I find out that there are 180 grams in 1 mole of glucose. Second question. It says calculate the number of moles of C6H12O6 in 45 grams of glucose. So now I start with 45 grams of C6H12O6. Notice how I showed my work. I put my grams of the substance I had, put a multiply sign, put a line, put the grams or the units that I have in a position where it's going to cancel, and the thing that it's asking for is the number of moles. So I'll put moles as my new set of units. Now, if you're confused about where we're going from and to, notice we're given a mass, and we're told find the number of moles. So we put moles as our new set of units right here, and we put the molar mass or the molecular mass from the periodic table on the bottom of that ratio. So I've got grams down here, and where do I get the number of grams of glucose there are in 1 mole? Notice I put 1 mole on the top, and the molar mass that I get from the periodic table on the bottom. And if I look back up here, there are 180 grams from adding up C6H12O6. So 180 would go on the bottom, and 45 divided by 180, I believe that turns out to be about 0.25 moles, or a quarter. 45 divided by 180 turns out to be 0.25 moles. Next question. It says, calculate the number of C6H12O6 molecules in 45 grams of the sample. Well, now I'm supposed to find a number of molecules. And if I look on here, I'm given a mass, and I'm supposed to find a number of molecules or particles. Can you go directly from mass to number of particles? Nope. I've got to go to moles first. And so this is actually a 2-step conversion, and we can use the relationship that we learned just from the last problem to help us out with that. So start with 45 grams, because they told us I have 45 grams. Put a multiply sign, put a line, put grams in a position where it's going to cancel, and make my mole as my new set of units, because notice I need to go from mass to mole. And when I go from mass to mole, I use the relationship of 1 mole to the molar mass, 1 over molar mass. And the next step, I'm going to go from moles to number of particles. And if the arrow is on the top here goes from moles to particles, I'll put Avogadro's number on the top and 1 mole on the bottom, which makes sense because I want that to cancel. So put your units in first. Put your units in first. Notice grams canceled with grams right here. Now put moles in a position where it's going to cancel, so put moles down here. And the number of particles I want, which happen to be called molecules in this case. So put molecules on the top. Now, where do I get this relationship? How many grams are there in a mole of this glucose stuff? Well, I use that relationship right up here. In 1 mole, there are 180 grams. Where did I get the 180 from? Well, I added up 6 carbons, 12 hydrogens, and 6 oxygens on the periodic table. Remember, carbon has an atomic mass of 12, oxygen 16, and hydrogen has an atomic mass of 1, and I multiplied it by the subscripts. Next, I'll multiply it by the number of molecules in 1 mole. And if I look, what's the number of molecules in 1 mole of anything? Well, it's Avogadro's number, 6.02 times 10 to the 23rd molecules in 1 mole. Now I can take 45 divided by 180, which is actually 0.25, times 6.02 times 10 to the 23rd, and if my math is close to right, I think I end up with about 1.5 times 10 to the 23rd molecules. And you too can do this without a calculator, because really when you're doing this, 45 divided by 180, you knew was 0.25 from up above here, but then take that 0.25 just times this first number right here. Don't worry worry about the e to the 23. That doesn't have anything to do when you're multiplying with it by 0.25. And a quarter of 6 is about 1.5 molecules. Okay, let's end with a couple of interconverting problems that add mass, moles, and particles all together. This one first says, determine the number of grams of glucose and oxygen atoms in 360 grams of glucose. So look at what we're given. We're given a mass. It eventually wants us to find the number of grams of glucose and the number of oxygen atoms. So we're first of all given a mass, and eventually it's going to want us to find the atoms inside of that glucose. To move from mass to atoms, we're going to have to go between to the mole. And actually, I think there's a little bit of a mistake here. I think this should say moles of glucose. Let's see if I can fix that before I give that to you as a handout. So we'll calculate the moles of glucose first, and then we'll look at the oxygen atoms. So in letter A, first thing we do is write down the number that we have, 360 grams. When you don't know what to do, at least write down the number that they give you. And it happens to be of glucose, which is C6H12O6. Write down the formula, put a multiply sign, put a line. Put the units that you have in a position where it's going to cancel, so put grams down here. And then we want to find out what the number of moles of glucose there are. So put moles as your new set of units. And we're moving from grams to moles. So look on this little diagram. And when we move from mass to moles, what relationship do you use? 1 mole on the top and the molar mass on the bottom. Where do you get the molar mass from? From the periodic table. Okay, so we put 1 mole on the top. C6H12O6 adds up to 180. Looks like that's the thing that we're using all the time for all these examples. So I put 180 grams here on the bottom, and then I would know my number of moles of glucose. 360 divided by 180, I think you can do that in your head. That turns out to be about 2 moles of glucose. In significant digits, of course, it'd be 2.00, because I think there were 3 sig figs in this. Oh, 4, 3.000. Actually, this might be my sig fig limiting thing, but it's close enough. Letter B. It says the number of oxygen atoms. So now we're going to go from moles, because we know the number of moles of glucose we have, to atoms inside of a glucose molecule. So when you move from mole to particle, we have to use 6.02 times 10 to the 23rd over 1. So we take our number of moles that we have. We have 2 moles of C6H12O6. Put a multiply sign, put a line. Put my mole in a position where it's going to cancel, and put my number of molecules of C6H12O6 as my new set of units. Notice I haven't gone to atoms yet, because there are 6 oxygen atoms per formula unit of C6H12O6. I'll have to do that next. So put another multiply sign and a line. And this time, what I'll say is that for every C6H12O6, there are a number of oxygen atoms. Where do I get that number? This little 6 right down here tells me that there are 6 oxygen atoms per 1 of the boxed formula unit right here. Moving back to this relationship, how many molecules are there in a mole? Well, if I look back at this diagram, what does it say? When I move from moles to particles, there are 6.02 times 10 to the 23rd. So this number right up here would be 6.02 times 10 to the 23rd molecules. So 2 times 6.02 gives me 12.04 times 10 to the 23rd times 6. And now I might need to use my calculator just a little bit. And let's go through how to put this in your calculator, just in case you're stuck on this. What I'd put in is 2 times 6.02, and then don't forget, I'm a fan of using the enter exponent key. Puts the e on there, to the 23rd power, and then multiply that by 6. So see how I used the enter exponent key right here, the e key, to take care of the times 10 to the 23rd. When I enter that, I get 7.224 times 10 to the 24th. So 7.224 times 10 to the 24th, and that would be atoms of oxygen. Atoms of oxygen. Okay, on the next page, there's one more sample problem like this. This is just a little bit different. It says determine determine the number of moles of CO2 and the grams of carbon dioxide gas in 1.5 times 10 to the 23rd molecules of CO. So start by writing down the number that they give you, 1.505 times 10 to the 23rd, and this happens to be molecules of CO2. And it says in letter A, first of all, the number of moles of CO2. And if you look at our little diagram right here, if we're given a number of particles, in this case a number of molecules, and we want to move to a mole, a number of moles of it, notice the relationship we use using this arrow, mole on the top, number of particles on the bottom, or Avogadro's number on the bottom. So multiply sign, put a line, put molecule in a position where it's going to cancel. Molecule right down here. This happens to be molecules of CO2. And then put mole as our new set of units. And in 1 mole there are Avogadro's number, 6.02 times 10 to the 23rd of these molecules. Okay? Notice my molecules will cancel with my molecules, and I'll end up with moles. And 1.5 divided by 6.02, you might be able to do that in your head, because if you double this, it's like 3, which is about half of 6. So this must be a half of a half, or a quarter. And it turns out that that is 0.25 times 10 to the 23rd. I'm sorry, the times 10 to the 23rds cancel. 0.25 moles of CO2. Sorry about that. I meant to show you that the e to the 23 would cancel with the e to the 23. They'd go away. And so you're left with just 1.5 divided by 6. Then 1.5 divided by 6 is about 0.25. So there's about a quarter of a mole of CO2, which answers letter A. Answers letter A. Okay, going on to letter B now. Letter B says the number of grams of carbon dioxide gas in this number of molecules. And if you look, once we know the number of moles, we can move from mole to mass simply by putting the molar mass on the top and moles on the bottom. Molar mass on the top, moles on the bottom. Where do you get the molar mass? Well, the molar or molecular mass is the thing that you add up on the periodic table depending on what the formula is. So take the number that you have, 0.25 moles, and it happens to be moles of carbon dioxide. Put a multiply sign, put a line, put moles in a position where it's going to cancel on the bottom, and then put grams as your new set of units, and it happens to be grams of CO2. Notice how the moles of CO2 and the moles of CO2 will cancel. And in 1 mole, how many grams are there? Notice on my chart here, I put 1 mole on the bottom, the molar mass on the top. And the molar mass I want to know is carbon dioxide, CO2. Carbon is 12. I'm just going to round it to 12. I'm not going to worry about the 0.01 right now. And oxygen is 16. And there's 2 oxygens. So 16 times 2 is 32, plus 12 more gives me 44. So there's 44 grams in 1 mole of carbon dioxide, and 0.25 of 44 is 11. So there are 11 grams of carbon dioxide gas in the 1.5 times 10 to the 23rd molecules of CO2. Notice the link that this gives us. This is the power of the mole. It allows us to take a macroscopic amount of carbon dioxide, one that you could actually see and measure with a scale, and link it to the number of molecules, the tiny, tiny particles that microscopes can't even see. The mole gives us a link between the macroscopic world and the nanoscopic world of atoms and molecules. Next videocast, we'll look at determining empirical formulas and molecular formulas, but good luck with your mole calculations from this videocast.